All right, so we've got the next here video for the calculus part 2 sample test. Here we're going to show that something is differentiable. Now, of course, we're just going to show this, not necessarily prove it. And so, in order to show that something is differentiable, it must first be continuous. Okay, now in order for it to be continuous, the limit as x approaches 5 from the left of the function must equal the limit as x approaches 5 from the right of the function, and furthermore it must equal the function when evaluated at 5. Alright, so if we evaluate this function at 5 here, we're going to get 3 times 5 squared minus 1, or 74, right? Now, just as a demonstration here, I'm going to just evaluate these limits with a table of values. Although it doesn't officially prove that it's continuous, it's what would be considered a, reasonable demonstration. Okay? Now, I don't have a calculator handy, but so here's our y values, right? Or we could actually call them f of x if you'd like. There we go. Or even furthermore, what you can actually do is you can even just write the entire function in there. A lot of times I'll do that as well. So the entire function is 3x squared minus 1. Right, because y is that, which is f of x. Okay, so basically what you want to do is choose values. So like 4.9 here, 4.99 and 4.999, and 5.1 right here, 5.01 and 5.001. Now, what we're trying to do here is we're approaching. If you think of this graphically, we're approaching 5. So, like 4.9 here, 4.99 and 4.999, and we're approaching 5 from the other side, 5.1, 5.01, and 5.001, and we're getting a series of points because we're going to plug them into this function. And what we'll discover is those points, as we find them here, will all converge on a specific value. Turns out it's going to be 74, right? Because this is the limit of the function here, 74. And so at 5, as you get closer to 5, the function gets closer to 74, and as you get closer to 5, the function gets closer to 74. And then when you're there, the function is 74, which is proven right here, which basically indicates that you have a continuous line right there at 5. And so since we're demonstrating continuity, that is our goal. Okay, so basically what you would do is you would evaluate these functions, these things here, and maybe you'd get like 71. I'm not going to type it into the calculator, but 71.12, and then you might get like 73.92, and then you might get 73.99, and you'd be like, yeah, that's pretty convincing. It's approaching 74. Over here, you might get like 78.72 or something like that. And then you might get 74.08. And then you might get 74.001. or something like that, right? And you'd be like, okay, of course, that is also approaching 74, right? And so since the limit approaches 74 from the left, the limit approaches 74 from the right, and the function itself is 74, then basically what you've got, or what we've more or less demonstrated here, is that the thing is continuous, okay? And now, in order for it to be continuous, we have to, in order for it to be differentiable, the limit of the derivative must exist. So we've basically concluded that these three are all equal to 74, and so therefore f of x is continuous at x equals 5, right? Now the question is it differentiable, right? Because that's what we're trying to figure out. Is it differentiable? So to determine differentiability, we have to do a further step, and we have to first find the derivative. So I'm going to go ahead and find f prime of x, which is going to be 3 of x plus h squared minus 1. Let me write my limit, f prime of x, the limit as h approaches 0, minus 3x squared minus 1 all over h. Okay, and I'll zoom in on this. I'm finding the derivative now. All right, so here's my first few steps. And so I've got 3 times x squared plus 2x h plus h squared minus 1 minus 3x squared plus 1 over h. Some canceling here. Some canceling is going to give us this and this, that and that. Some further canceling is going to give us, let's go with purple or something. We can cancel this h with that h and that h, only because there's no other terms with h's in it. Okay, and so we've got f prime of x equals the limit as h approaches 0 of 2x plus h. Now if I let the limit, if I let h approach 0, I'll go ahead and write 2x plus 0, which is 2x. So we've basically demonstrated that f prime of x is 2x. Okay. Don't forget that when you finally do apply your limit here, you shouldn't write it in the, so limit as h approaches 0. You don't want to write it again now because you've actually let h approach 0 here. And so you would actually get rid of it there at that point. All right, so we've basically determined that f prime is 2x. All right, let's go back to the original question here. Original question was show that it's differentiable. Well, we've already demonstrated that it's continuous. Now we want to demonstrate differentiability. Now, in order for something to be differentiable, the limit as x approaches 5 of the derivative should equal the limit as x approaches 5 from the right of the derivative itself. Okay, and so let's go ahead and do that. Give us some space here. So again, just to determine the limit, I'm going to use a simple table of values. The trick is, in this table of values here, I'm going to use 2x, which is the derivative, right? Oh, shoot, I messed up big time here, because the derivative is not 2x, it's 6x. I messed up here. Look at this. There should be a 3 here distributed in. Let's go back to this derivative. This guy is a 6x, right? And furthermore, there's actually a 3 here plus 3h squared, giving us a down here something much different. All right, so it's 3x. Sorry, no, 6x. 6x plus 3h. And then we're going to go ahead and do 6x plus 3 times 0, which gives us 6x. Nice. All right. Sorry about that. Now, the reason why is because this 3 here, I forgot to distribute in to the resulting x squared plus 6x plus 3, all of this stuff here, right? All of this stuff in this area. So that was a algebra error. But now that we've got that, the derivative should be 6x. Okay, this derivative here is x and 6x. Now I'm again approaching 5 from below and above, and I can just use the same numbers. 4.9, 4.99, and 4.999, 5.1, 5.01, and 5.001, right? And now I'm basically plugging 5 into this function here, 6x. So I'm going to get something around 30 here, right? As it appears to be 5 times 6 is about 30. So over in this area, you're gonna plug this in your calculator, and you'll see that this is like 29.999. This is gonna be like 30.001. These ones here are gonna be like 29.9, whatever, and 29.8. Let's say, I don't know. I'm not gonna go 28. Sorry, this one over here is gonna be like some just above 30. So 30.1, although it's not quite right, but it's 30.01, and then it's like 30.001, right? So in this case, you can see that both of these are approaching 30. Since these are equal, you've demonstrated that the limit of the derivative exists, essentially, or left and the right hand limit of the derivative are equal, right? And basically, together with the fact that these, let me zoom in here, or zoom out, sorry. What we've essentially demonstrated here is that this yellow bit and that yellow bit, which I'll re-highlight now, first it's continuous, and then the limit of the derivative exists. Basically, we've demonstrated that it is differentiable, right, up here. And just as a quick note, this, like I said before, shows that there's no breaks in the line, and this shows no bends in the line. Or what I mean by bends is sharp bends, actually. Like something like this. Like you wouldn't be able to take the derivative there if this were a function f of x. And if the function looked like this, then your left and your right hand limits would be different. For example, the limit here would be some positive value. Here it would be some negative value. And these two limits wouldn't be, for example, both 30. Okay? All right, so now let's go to the 9th question here. Use the first principles definition to find the derivative. So this is that one that I just did, and this time I'll try it without making any mistakes. The limit as h approaches 0 of x squared minus 1. Oops, already made a mistake. X plus h squared minus 1 minus x squared minus 1 over h. And you end up with the limit as h approaches 0 here of x squared plus 2xh plus h squared, and there's nothing to distribute. There's no 3 here, so I'm okay. Don't forget that 3 in the future, minus x squared plus 1. And this is all still over h. This x squared and that negative cancel. Oops, forgot a minus 1. Minus 1 minus x squared plus 1. This minus 1 I forgot. Now it's there. See, it's easy to actually fix any mistakes that you have because you're expecting something to happen, right? So I was expecting that plus 1 and that minus 1 to cancel. And I said, oh, where's that minus 1? You can go back and you can check it. This h cancels with those pair of h's up there. And you end up with 2x plus h. So the limit as h approaches 0 of 2x plus h is simply 2x. And there's our definition. Our derivative. Okay, that's A. For B, if I'd like to find the equation of the tangent line, it's going to be f of 2 minus, sorry, that's not correct. It's y minus f of 2, which equals f prime of 2 times x minus 2. This is the linear formula for a point slope form, and that 2 happens to be the location where we're attempting to find the tangent line. This is a pretty easy procedure. I just evaluate the function at 2, so it's 2 squared minus 1, or 3, and I evaluate the derivative at 2, right? So 2 times 2. And when I evaluate the derivative, I'm going to go ahead and put a 2 there, but notice I'm putting a prime right here, indicating that I'm evaluating the derivative, okay? And they're giving us a 4, right? And so basically, what are we looking at here? We are looking at the tangent line. So it's y equals, minus f of 2, which I know f of 2 is 3, y minus 3, which equals, I'm actually going to go ahead and put f prime of 2, which happens to be 4, and then x minus 2 right in there. All right. And there we have it. This is our tangent line. This guy is this guy, which I discovered here. And this guy is that guy, which I discovered there. And there's our tangent line for that one. Now graph the tangent line on an equation here. I'll go ahead and pull up Desmos. There we go. I'm going to start graphing. And here, our original function was y equals x squared minus 1, if I remember correctly. Right, y equals x squared minus 1. And now here's my tangent line. Oh, sorry, actually, here's my tangent line. Y minus 3 equals 4 times x minus 2. This should produce a tangent line at the location x equals 2. Okay, so going back to this graph here, comma. So there's where I'm looking for my tangent line to be, right? Right there at 2. You see it? Now, if I graph the line that I just produced, which was y minus 4, I believe, equals 3. No, it was y minus 3 equals 4 and x minus 2. Boom. There we have it. That green line, which is this line right here, that green line is a tangent line exactly at 2, because I've got the point, which is 2 comma 3, right? This one. And then the slope of this line happens to be 4, right? If I just make a regular line of slope 4 here, a regular line of slope 4, it's going to be y equals 4x. Look at that orange line has a slope of 4. If we're looking at points, slope-intercept form, the green line also has a slope of 4. And there's the slope right there. Anyway, so that's how you would graph those. I believe you were asked to graph the derivative as well. And I think basically, if you want, you can do just a new function here, y equals 2x, right? That's the derivative here, okay? If I remember correctly. Yes, 2x. All right, so that's basically what we're going to do there. All right, thanks for watching. If you have any questions, you can just kind of go back there.